Yes, hello from the two of us, and thanks for allowing us to be part of this experiment. And the two of us have the privilege that we have been working together for quite a while already. So we are not a new team, but we have had some time to think about these things, which still means that it is very much work in progress. And we will proceed in the way that we will, during the talk, switch from the one to the other whenever we see that that might be a good idea. So that was the plan. What we are dealing with is the classification of mathematical objects, and we all know that that has been on the minds of mathematicians from the very beginning. Just think of the classification of the Platonic solids in Euclid, or Newton's work on the classification of cubic curves, or the classification of crystallographic groups. So there are many instances. And when it comes to groups, group theory as a field, we have touched on it already, which is nice, began to emerge in the late 18th or early 19th century. And basically what we have is two types of groups, finite groups and infinite groups. And in the 19th century, the fundamental and quite far-reaching question arose of what the building blocks of finite groups might be. And the explicit call for a classification of these building blocks, the finite simple groups, was first expressed by Otto Hölder in 1892, who said, well, it worked a minute ago.
Yes.
Okay. So who said it would be of the greatest interest if it were possible to give an overview of the entire collection of finite groups. So that is Hölder's research program of the classification of finite simple groups, meaning the idea of being able to present them in form of a list. And this was carried out in an unprecedented collaborative effort of group theorists around the world between 1950 maybe and 1980. And the final classification theorem can be elegantly summed up in a few lines, and that's where Rebecca now takes over, because she is the expert in group theory.
Now it works. Thank you, Volker. Yes, the previous talk made me very happy for various reasons. One of them is that we touched on the origins of group theory. So when Hölder phrased his invitation, as we call it, a lot of simple groups were already known. I will get to this in a moment. But let's look at this classification theorem now for just a brief moment without going into technical details. If you are interested in technical details about the groups and everything around that, please feel free to ask me later. Now, the theorem says that every finite simple group is isomorphic to one of the following types. It could be a cyclic group of prime order, infinitely many, because there are infinitely many prime numbers. Then it could be an alternating group of degree at least 5, again, infinitely many subgroups. Then it could be a finite simple group of Lie type, again, infinitely many. We have lots of families, and they are infinite in two ways. You could change the dimension, and you could also change the underlying field. And then we have 26 sporadic simple groups. Now, when Hölder phrased his invitation, 5 of these 26 sporadic simple groups were already known. It's surprising that he doesn't mention them in his article, the 5 mature groups. Of the infinite families, a few were known already by that time as well, namely the cyclic groups of prime order and also the alternating groups, and some of the finite simple groups of Lie type, going back to work by Jourdan, for example. But then, for example, the 21 still missing sporadic simple groups, they were found much later, within roughly 10 years, from roughly 1965 to 75. So there was a long time when it was not even clear whether there would be more sporadic simple groups. And if you look at this theorem now, then maybe you notice, as opposed to many other mathematical theorems that you might see, there is not a name or several names. There is not a year that is attached to this theorem. And these are just two interesting bits about this enormous theorem. Also, the simplicity of the statement is very much misleading because a lot of complexity is hidden just in the names of the groups, the distinction into the families. There are many, many more very special things about this theorem. For example, that you don't have just one statement and then it's a paper and you have the proof and it's just in this one paper or this one book. This is not the case here. The proof at the time of this statement was scattered across many, many books and articles and partly even unpublished work. And there is an estimate here between 10,000 and 15,000 journal pages. Many, many publications. So it's spread over a lot of publications of different kinds with different notations from different parts of group theory. Many, many mathematicians have worked on that. And here we only see the time period that we focus on, 1950 to around 1980. There is, of course, more that has happened before that laid the foundations for a lot of the work that was done here. And not only is it scattered, but also the work is so deep that it's not even clear at the time of this writing that a single person would be able to read, understand, maybe even check all this work. So this is definitely something very special about this theorem. We are interested in various stages of the classification. One of them is this stage when the efforts towards the proof of the final statement seemed to come to an end for the first time. So here we quote from Ron Solomon, "The bell tolls for the classification." This is in the 70s. We have lots of comments around this. There was a conference, the Duluth conference, where there was a felt sense of, we are getting close, this is almost finished, which is surprising because a few years before that, there was no such sense. So psychologically, we think it's very interesting to study this period of time further and in more detail. Psychologically, this is what this article says from one of the main players in the classification. Psychologically, it was over in 1976. And we have one original quote that confirms this felt sense, namely from a letter from John Alperin to Walter Veit. We found this in the Veit papers at the Briscoe Center in Austin, Texas. Here we see in the middle, that convinces me that the ball game is over, with many, many exclamation marks. So this is one of the few original documents that we have where from the time we see that someone actually thought they were getting close to the end. Because it's always easier to say in hindsight that you knew that the end was coming, right? Okay. Then, in the early 80s, the first generation proof was announced to be finished. And there's even a famous quote, "It's all over now." And we see how this affects the community of young group theorists at the time fairly heavily. But, as it turned out, this announcement was premature. It turned out that there was a major gap. As I said, the proof was scattered, manuscripts, unpublished work, and this turned out to be a problem. And here we found an original document telling us how people became aware that this is really a problem. This is from a letter, again, November 1991. Again, we found it in the Veit papers. And here we see that we explicitly find a written concern that there is a gap. The quasi-thin case, and if you're interested, I can tell you what this is. The quasi-thin case was claimed to be done. There was a manuscript, but in fact it was not done. The manuscript was not complete. There was indeed no proof for this case. And Danny, the person who's mentioned here, that's Danny Gornstein. We will hear more about him later. Now, the gap was closed much later, 2004. There were little bits that also needed to be tidied up. So if we're really strict, then we should say that the first generation proof was finished in 2006, much later than the official announcement. And you can see how this raises the question of, do we actually have a proof? We had this question earlier today. What is a mathematical proof? Is it a proof if it's scattered around thousands of pages and there is no coherent notation, no coherent strategy? Is this actually a proof? So from the community itself, there was this concern and there was this desire to have a more accessible treatment, a more readable treatment, something that would actually be accepted as a proof. And this is still ongoing. There is one more blue book in the series that we photographed there, and more books are on the way. So it should be finished soon, and we will hear more about this and the self-historicization that comes along with it from Volker.
So reflections about the history of this project are scarce. Most of them come from the major players in the field, which is fine, which helps us a lot in assessing what was going on. You can see that here, especially Gorenstein and Solomon were very active there. But when it comes to, I wanted to mention there are even two quite readable monographs on it. They are not perfect, but they can give you a good orientation. They really make a good read if you are interested in this bedside reading, really. And there is another interesting thing about the community, because they began to be interested in their history themselves. In the late 70s, Joseph Gallian, we'll meet him later again, who is a group theorist, but not from this classification community, carried out an oral history project called on the classification of finite simple groups around 1980. No publication has come out of it, but some of the interviews are accessible in the Briscoe Center in Austin, Texas. Really very helpful. And these interviews really show that a large number of mathematicians was part of this whole enterprise classifying the finite simple groups. But what we not really have is work on the history of the classification theorem from the perspective of history of mathematics or history of science. This is slowly changing. Alma Steingart made a start of it 12, 13 years ago. And just a few months ago, a PhD student of Rebecca Atle-Höhne, he produced a PhD thesis about the question of the sporadic groups. So it's a wonderful piece. And we are about to start publishing on this. But as of now, there is no historical treatment from a perspective of history of mathematics on the classification of finite simple groups. And that is really the gap that we too want to start to fill with our joint project over the next 2 decades or so. It grows larger every day in a way. And when we started to work on this together 2 years ago, we had 2 priorities. In an initial phase, which is about to end, we decided to restrict ourselves to a set of core questions we might deal with, but especially address the time-critical task of securing relevant material. So above all, preparing and conducting in-person interviews with players of this project, and Rebecca will come back to that later. I would like to mention that this joint work in this first phase of the project has taught us a lot. What about the scope and the difficulty of the project? Also that we can function as a team, which is helpful, because that's not, well, you all know that is not something you can really build on when you decide to embark on such a thing. And we realized that the combination of our qualifications as group theorist from the community with contacts into the community and historian of science mathematics was really fruitful. So we think this first phase was a really good start. And now the second phase is about to begin, and we want to thoroughly analyze the history of the classification in its various contexts. So the work is coming now, in a way. And we want to use the history of the classification as a magnifying glass, in a way, to draw conclusions not only about the history of mathematics and the mathematical community in the context of Cold War science, but also to relate these conclusions to the history of Cold War science in general. So we think we can make a point that goes beyond mathematics and history of mathematics, and personally, this is very much on my agenda to make historians of science realize that we do interesting work in history of mathematics. It's very often just overlooked, I think. And for instance, we realized that the history of the classification can be seen as an excellent example of the impact of politics on research in pure mathematics in the Cold War, namely via new possibilities of funding research in general and mathematical research, and especially also research in pure mathematics in particular, which is rather unexplored territory, but we think it's crucial for this classification project. Yeah. And when we further developed our approach, we realized that we should work in the form of case studies, because this is so huge, it will take 2 decades, but it would be nice to every once in a while be able to present a result, and Rebecca will go into that now.
Yes, thank you. The first case study has already been mentioned. This is the work of one of my most recent PhD students, Atle Höhne. He has written a fantastic PhD thesis about the history of the modern sporadic simple groups. And he has excellently developed his work along some of the principles that we will explain later, so that we have something like a gold standard now for a lot of the work that is still coming. So this is wonderful. Then along this, parallel to this, we would like to study the history of the classification of the finite simple groups of Lie type. This goes far back. I already mentioned Jordan, for example, but then there's also a more modern approach, and we would like to really understand what's going on there and how different fields close to group theory have informed this classification and the language that was used. I have a student who starts working on this, and hopefully this will become his PhD project. Then we would like to shed some light on the history of German immigrant mathematicians that played a role, for example, Richard Brauer and Reinhold Baer. And finally, we think that psychologically the end of the first generation proof is very interesting. I already mentioned this. The impact on the community is very interesting, and interviews show that this is really a very relevant line for our research. But also, while the classification project happened, computers started to play a role in mathematical work, and we would like to understand this better, along with the development of computational group theory becoming a branch of mathematical research itself. And we hope that we will get more funding for our project. If we get it, then it will be easier for us to include 2 colleagues who are experts in this area and can help us. And I would like to name them, namely Martin Bulling from Paris and Lisbeth de Mol from Lille. Now, from our original themes, I only want to mention them briefly. We have the changing nature of proof in mathematics. I already mentioned how the unsurveyability of the original proof plays a role in how we view this project, but also maybe how it is viewed from mathematicians from other areas of mathematics. Do they even trust the existing proof, if it even is a proof? So changing nature of proof. Then the role of self-historicization, Volker will tell us about that, and also big mathematics as a concept, which we use to study the history of the classification. And I want to just briefly touch on this. I already mentioned surveyability for the classification, for the original proof. I think we have 2 layers of unsurveyability. One is the sheer size, the notation that is not consistent, and the fact that a lot of the work has originally not been checked, or it was hard to be checked because there were long, very technical papers. Sometimes work was used from PhD thesis. Sometimes in the references you see private communication. This is a big challenge. Plus, we have the use of computers. And for us now, it's often hard to understand where computers were used, who wrote the code, how was it written, is it even accessible for us now? So there are huge challenges there, and I already mentioned that we would like to go into the second aspect further. So we have 2 ways how we can look at unsurveyability of this proof that we would like to follow up on. And now I hand it over to you.
I just say a few words about the role of self-historicization. Many of you may be aware of the fact that writing the history of a discipline as it evolves, or of a result as it evolves, is of course may be crucial to lend credibility to the result, especially when, in this case, where it's a result where you could have your doubts about it. And in the classification community, this idea to historicize the classification project started early. Daniel Gorenstein, I marked this here in blue, Gorenstein and Solomon were the first to really deal with this in print. Others have historical notes in their papers. So that is really very interesting. And as I already mentioned, there is this remarkable project from within the community that Joe Gallion instigated. So the idea was to collect sources for the history of finite simple groups, modeled after Kuhn's project, and there was a contemporaneous project by Spencer Weird, Sources for History of Modern Astrophysics. So this came from the community, and Gallion started to do interviews, but as he didn't get funding from the National Science Foundation, which in itself is very interesting because that shows who defines what history of science is in 1980, and history of science is history of physics in 1980. So this is a very interesting project, and we think that we should further analyze it in the context of a need of legitimization of the result, because that was not so clear around 1980. So produce a success story is really the guideline here. The third main theme, and we want to spend the rest of our time on that today, is big mathematics. And this is has proved to be a fruitful way for us to access the history of the classification of finite simple groups. And to be clear, part of what we do while we follow this project is reassess in what way this concept can help us understand things and in what way it might be useful. So can it be a useful concept for the history of 20th or 21st century mathematics? And I would like to explain this a bit. We already heard that there was a huge amount of people dealing with classification of finite simple groups. I think Gorenstein mentions 100, other estimates go towards 300 people being busy on this one result in a way. Many of them enrolled by way of PhD thesis, so problems being handed out and being solved by young mathematicians. So the sheer size of this is probably without precedent in the history of mathematics. And in 2005, E. Brian Davis characterized the classification project as industrial scale pure mathematics. And when I came across that quote, I thought, well, when it comes from within the mathematicians community that they say this is industrial scale, why not think about big mathematics as a concept rooted in ideas of big science? So what we propose here is adapted from characterizations of big science from the last 20 or 30 years or so. And big science, of course, in itself is an extremely heterogeneous concept. Ask two historians of science, they probably not agree on what big science entails, but there are sufficient intersections to really work with that, I think. And recently, historians of science, John Aga and Naomi Oreskes, have further refined this. So I think we can work with this. It will help us as an analytical category, and we think that it will help us to put the classification in various contexts, such as the role of Cold War science and in general the impact of politics on the development of pure mathematics in the 50s, 60s and 70s. As I already said, especially the new possibilities of funding are striking here, and we found it very striking when working on this, how much money went into here. I think we'll come back to that. So currently, we have 5 we use a concept of big mathematics with 5 defining features to structure our project, namely as a geographically widespread, teamwork-oriented, resource-intensive project relying on large equipment and at some point necessitating a central strategy and coordination. So that are the 5 things that it's in a way our checklist, and it's not ordered by importance. So we could start with teamwork-oriented, blah blah. It's volatile in a way. So I would just want to quickly mention it was indeed geographically widespread, but we face a challenge here because our current literature review shows that a substantial number of publications comes from the former Soviet Union, which we find surprising because this is not reflected in the 9-volume blue books that Rebecca showed earlier. So the trace of the publications from the Soviet Union, well, it seems to be petering out in the tradition we can see. So this is a topic for further investigation, and we have started this work with 2 students who are able to speak and read Russian and who now, together with Rebecca, begin to find and translate articles that have not been accessible for us as of now. So we are building this Russian language database too. In what follows, I'll cover some aspects of characteristics 3 and 4, and Rebecca will concentrate on 2 and 5 after that. So the classification as a resource-intensive project, of course, we do not speak about resource intensity in terms of physics or biology, where you have large labs or you have a large hadron collider consuming immense amounts of money. But we think that the combined effort behind the classification needed a substantial amount of resources that was really beyond that, but the tiny amounts that you need as a lone mathematician having a blackboard and some chalk and paper and pencil and maybe ribbons for your typewriter to type out the formulae or so. So if we compare the cost of average activities in mathematics in the 50s, 60s, and 70s, then the budgets of some of the major conferences and year-long events in the classification project are really amazing. We are talking about hundreds of thousands of dollars, which is going back to the 50s and 60s, rather striking. And the problem that we have now is that it is difficult to quantify this cost. We know some of the agencies that put money into this, the National Science Foundation, of course, the Air Force Office of Scientific Research, the NSA, etc., etc. So there's a lot of somehow military money going into this, but detailed information and historical work on the scope of military patronage or funding of mathematics is still scarce. So we are trying to build this up on the way here. However, information we have indicates that the context of the Cold War really opened up new possibilities for funding on a large scale. And one example is this application for a group theory year at the Institute for Advanced Study in Princeton. Armand Borel was behind this. He was very much interested for a while in the classification project. And so this is an application to the Air Force Office of Scientific Research. And we see the right people here. It's Bernstein, we meet him again. It's Brauer, it's Dauberman, it's Janko, it's Suzuki, it's Thompson, it's Titz, Alperin down here, etc. So this is really, they're all part of the in-group. And the budget, the estimated budget is $130,000. So we are really talking about rather huge amounts of money here compared to the usual business. And there were these funding opportunities. The next point I want to mention shortly is large equipment in the classification. Again, we do not want to compare this to large equipment in terms of a Large Hadron Collider, naturally. But what we know is that computers, as Rebecca said, became increasingly important in this classification project. And even though we might tend to forget that, they qualify as large equipment in the 50s and 60s and even in the 70s. And when proving the four-color theorem in the mid-70s, Appel and Haken used 1,200 hours of computing time on 3 different computers. And that was when computing time really was still expensive and not everyone had access to these computer labs. A crucial perspective on the resources needed is both the cost of computing time and the availability of the computing facilities in the 60s and 50s. And to give one example, Charles Sims, one of the central players in the chase for sporadic groups, looking back on his contributions to constructing these groups in 1978, commented on the role of computers and the ensuing costs. With respect to the construction of the monster group, that's the largest of the sporadic groups with an order of roughly 10 to the 53. He explained, as you read, these rough calculations indicate that the construction of the monster is technically feasible, but not yet economically justifiable. So here we really see this money and large equipment aspect. There is a computer-free construction of the monster group published by Grice in '82. But this leads to what Rebecca already mentioned. We would really like to better understand the role of computers and computing facilities in the original proof of the classification theorem, and how this was discussed and reflected on in the community, because we can see that this was a topic naturally. So that's where I hand over to Rebecca again.
And yes, we have 2 aspects of big mathematics left to discuss. One is that it was very teamwork oriented, as we can see, and you can check it very easily by just checking the publications. Many of them are by several authors. Also towards the end, if you look at the efforts to write articles about the current status, then you also see all these names mentioned. So it's clear that a huge number of people was working together there. But then it could be independent work that comes together, or it could be actual teamwork. And we have a lot of evidence for actual teamwork. So here, for example, this is about the group theory in Chicago, 6061. Again, it needed a lot of resources. But for example, what you can see here, so there's lots of interesting things on the slide. At the very bottom, you have funding information that is interesting, the Air Force, the ESO Foundation, but we already talked about funding. You see that the odd order paper, one of the milestones of the classification project, was partly written there during this year. So it was an opportunity for people to meet and to work on a part of the classification program together for a longer time in a very focused way. What I also want to mention is, yes, so here there's an original quote from Ron Solomon that I want to show you. First, real science appeared of the evolving sociology of the classification effort as a team project. So this is more than just people working on different parts of a project, and in the end it comes together. It's actually a team effort, and it becomes more and more of a team effort the longer you look at the project. In the 70s with Gorenstein and the strategy, it really becomes a project for a big group, and we will touch on the strategy for that in a moment. How important teamwork was and how important the community was, and community in a broad sense, also becomes apparent in the interviews. So what I show you here is a list of people with whom I conducted interviews that were recorded. I also had informal interviews, a lot of off-the-record discussions. And here you have a variety of people. You have people like Michael Aschbacher or Richard Lyons who were in the middle of it. So talking to them, of course, is crucial, as long as they are still around. I was not able to talk to some of the people who were in the middle of things because they are no longer with us. With some I spoke, but it was before the official project started and I had a guideline for my interviews. So it's really difficult to have these conversations, and I will talk about that a little bit more later on. But now I just want to show you how that we have this diverse group of people, main players, people who were a bit more on the outside, people who did something else but were at a place where a lot of classification work was done, and therefore they saw a lot of it, and they can give us a bit of an outside view. And the list is growing. So in these interviews, we find more evidence of the various qualities of teamwork and how friendships were established. So colleagues worked together and became friends, and they were solving problems for years and years and years. I also want to mention the Oberwolfach Institute that played a major role. Sometimes special cases of theorems that became important for the classification were discussed there. Again, the famous odd order theorem, a special case was discussed there during a meeting, and we even have a witness who was there and who told me how exciting it was to be there at this time. I already mentioned the group theory here in Chicago. We saw the IIS in Princeton that played a role. All this happened during a time when conferences became much more common in the mathematical community as a whole, and we can see the effect on the classification project. Now, this ties in with what we call a central strategy and coordination, because when you look at the early results about the classification, then you have special cases, you have types of groups that are classified in various ways, but there is nothing going in the direction of, so how do we find them all? How can we be sure in the end that we have found all the groups? I mean, if we keep finding more, how do we know that we don't just keep finding more, right? In particular with the sporadics. Yes, it's exciting to find a new group, and then you become famous because your name is on this group. So people keep looking, but then how do you know that it will eventually stop? What if it doesn't? What is a strategy to show that you have actually found all the groups? And this is a difficult question mathematically, but also logistically. How do you collect all the information that you have in one place? It's not possible for one person to read all these papers and to keep track of things. So for a while at least, Danny Gornstein, whom we have seen before, he was a key authority in the community. He was one of the people who believed that it could be done. And maybe this was, for a few years, his main role. He was crazy enough to believe that you could design a program that in the end will give you a proof for the classification theorem. And let's not forget that the classification theorem evolved along with its proof. You didn't have a conjecture and you just need to prove it. No, the theorem evolved along with its proof, which is again something very unusual. So Danny Gornstein was trusted by the group theory community, by many of them. We have evidence of that from many interviews and also by some accounts in writing. And there are many names for him. For example, people call him CEO of the classification project, godfather, coach of the team, captain of the team. He was often described as a force of nature, a charismatic person with a lot of energy and chutzpah and just, moving forward and encouraging the community to keep going. And I think that he was one of the driving forces behind the change of psychology. In the early 70s, he presents his program showing a way, like a big strategy, how the theorem could actually be proven once we have hopefully found out the groups. But then he was also the person who believed it could be done and who encouraged just enough people, just a critical mass, so that things started moving. And then enough young, talented, enthusiastic mathematicians joined the team and proved special cases and proved big cases of the central strategy so that more people started to believe it could be done. And then within a few years in the 70s, we see this shift from it's a pipe dream to we are basically done. It's amazing, I think. So he was the architect of this. Interestingly, not everyone in the community sees his role in the same way. So this is another thing that we hope we can find out more about in the interviews. And this brings me to some final comments. Interviews are challenging, yes. We have to identify all the people who might be interesting for us for interviews, and that's not easy. I mean, where do you stop? Some of these people are already very old. It might not be possible to talk to them in a reasonable way. I have to prepare mathematically before I talk with these people. And yes, I know many of them personally, but not all of them. And sometimes it's a little bit awkward to have this first contact. And I needed to prepare myself very much for the strategy, for the interview, for the questions, and also for the mathematical content, because if I ask the mathematical questions, I should know exactly what I talk about. And then there's the aftermath, providing transcriptions, checking on details, checking things against other interviews, because it's the memory of living people. Some of them are really old. So, of course, you will have contradicting statements. Opinions on the equipment, the importance of results, the contributions of people, the importance of, for example, the strategy by Danny Gornstein, these opinions vary vastly. So maybe we went into this thinking, oh, if we just interview all these people, then we will get a coherent picture of what was going on. No, of course not. There are so many people, and we see changes in generations, in regions, in schools of thought. So it's still very interesting, and I will talk to more people, and I'm sure I will learn many new things about the opinions that people have on the project, all the way to, do we have a proof or not? Even within the community, they don't all think the same about this. There's a lot of room for misunderstanding. For example, when we started talking about this perspective of big mathematics, we were often misunderstood, and people thought, oh, so you mean important mathematics and the rest is not important? No. So you mean big in terms of impactful theorem? No, not necessarily. Oh, with the criteria, you organize them by priority? No, not necessarily. So a lot of clarification still has to be done, and we keep learning about the potential of this approach, but also the boundaries, the restrictions. I would like, so this is part of my personal mission in this project, I would like to make more visible the contributions that have not been visible so far. Maybe a young PhD student who solved a special case that was later never quoted because someone famous did something more general. Maybe someone who wrote code in the early days and it's just a footnote somewhere and later it got forgotten. Maybe a person who gave someone an idea for a proof of a theorem and then was never mentioned. Visibility. This is one that is close to my heart. Joe Gallion and his efforts have not been visible enough, we think. So we hope that our work can make people like him and their efforts more visible as we are progressing in our project. And then this work has forever changed my teaching. And this conference is another example of how this happens. So I sit here, someone talks about Fermat's little theorem and about a special case, and I'm thinking, oh, I will teach this soon, and I want to tell my students about the special case and about the history behind that. So I will never teach the same. I will never teach as I did before I started working with Volker, and many of my students really love it.
Yeah, there's really just one point left, and I think we explained that. This idea of big mathematics is really, really helpful for us as an analytical framework. It helps to make compartments out of this rather large project, and it really helps to, see some things that you don't see when you just have this bulk of big mathematics or tons of papers and people involved in it. So it really helps us to organize the field and what we think about it. And of course, if you relate it to Cold War science, it makes it easily relatable, I think, to ideas in history of science in general.
Do you want to talk about the NSA advertisement that we saw?
Yes, the NSA, I think we have it here because that's our extra.
So this was a big surprise.
Yes, this We Want You. This is a message of career interest to the advanced creative mathematician from NSA. You won't be surprised, it's from the 70s, but it's clear. Why do they put so much money in this classification or in pure mathematics? Because they need PhDs who could, in the event of a further confrontation with the Soviet Union, be helpful in having the mathematical expertise that you need for wars in the 20th century.
And so approached people from the investigation project specifically. We have quite a few accounts of that.
Yes, or they approached them in Princeton at these special years. There would be an Air Force officer approaching people there. But that's about what we wanted to tell you today. Thank you.
Thank you.
So shows
I was very interested, thank you very much for the talk. I was very interested in the Soviet part of what you have presented and of the Cold War aspect. The background for this is that I have a PhD student who is working on the Cold War case, completely different one, but I think it's going to be interesting for all of you to talk to each other. So I wanted to know whether, for instance, some of the papers on these issues that were written in Russian were translated into English in this attempt to have a kind of surveillance of what was happening in Soviet Union that was in the translation of the Russian, I forget the name of the American journal that was publishing translations into English of Soviet. And I wanted also to know about precisely how people were looking at each other, how people were observing each other, how knowledge circulated between both contexts, because you have teamwork and you have people across the Iron Curtain, and you have all this intelligence idea behind in the background. So how did knowledge circulate? And for instance, it was very striking for me that you mentioned the year 1960, 1961, which is shortly after the Sputnik thing. So what about this context? And
maybe I briefly start. So I know of mathematicians from the eastern part of Germany who were able to go to Oberwolfach and then have some exchange. I don't know much about mathematicians from further east, but we are trying to find out. We can look at the Oberwolfach conferences. So there is this time where they want to be very international, but I think it goes more in one direction, not in all directions. But maybe you can say more about that. We see some mentioning of names, we see some citations, but it's not very much, and then often it's much later. So sometimes I see so many papers and their titles look like, this is classification relevant, and then I check the citations and there's nothing in the relevant time. Maybe there's nothing forever, or maybe it's much later. And then I wonder, how did this happen? And therefore, we now try to look at translations or to translate ourselves, because I want to see whether I can find evidence that this work was actually inspired by the classification. Because if we find, oh, I read this and there was this question, then at least we can tie it together in one way. And then the next question is, why was it not seen and cited and received on the other side of things, so to speak, to make it very easy with two sides. I know this is not complex enough. But we think that understanding the papers and reading comments about funding, about inspiration for questions and references will be a first step to understand this. And then we have to see where we can take it from there. It's really difficult. Yeah. Okay.
And your question is a good instance of what we know, that as of now, our project raises more questions than we can answer. That is really, we have tons of open questions, and this is one of them. Yeah. Because it's difficult to assess, of course. This might be one way into Waldecker.
Yes, allow me a technical question. I know that recently there's a language called Lean, which is used for proof correction, now checking, is being tied up with artificial intelligence to go through important theorems to check. They've done it with prime number theorem, Carlson theorem on Fourier series. Do you know if this is being applied to this situation?
I know that people are working on this, and so, for example, the odd order theorem has been done. There has been some automatic proof checking in some way. Since the classification proof is so large, it will take a long time, and I guess maybe not everything can be done with the same program, the same language, the same infrastructure. But yes, people are thinking about this and working on that, and I'm curious to see what happens.
What is the question about? Only question, maybe more than you can handle. What close webinar.
Thank you for your presentation. Yeah, I have just one question when you speak about Gorenstein. You said that he starts a program, but what does mean a program? Is that the same meaning that the Erlangen program of Klein, or is it a program with really a plan? That's something we see that the first step is that, the second is this one, and so on, or it's just he raised the question and, as you said, work as an authority and not really give a strategy to solve this problem. Thank you.
Yeah, there's even written documentation about that. So this was in 1972, and it's a detailed program where he explains how a case distinction can be made. So I can give you as many details as you want, but I will try and constrain myself. The proof is a proof by contradiction. So here's the theorem of the classification. Assume for contradiction that we have another finite simple group that is not on this list. And then you begin to do a case distinction. So you have this group, it has finite order by minimality, so by choosing a minimal counterexample. So you find a group that is not on the list, you choose it to have minimal order. And then because of the minimal order, you know that whenever you see a substructure and you see something finite and simple in there, it's on your known list. And then you can start to make arguments following that by a case distinction. So the prime number 2 must be a divisor of the order of the group, so you can do a lot with the prime number 2. And then you can do lots and lots of things. There are so many techniques and methods, but you need someone who gives you basically a roadmap, a case distinction. First you do this, so maybe it's that group. Oh, no, it's not. Oh, then you try this. Maybe it's that group. No, it's not, blah, 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 until you reach a final contradiction. Gorenstein set up such a path. And he gave evidence, because of special cases that had already been done by him and others, he gave evidence that this might be a suitable way to approach the problem. Because if you do something that is so massive and you think it takes 20 or 30 years, or it's not even feasible, then psychologically it's a good idea, and I think he was clever that way, to give evidence that this is a good strategy. So he said, oh, this is what we have to do, case 1, case 2, 2A, 2B, 2C, blah, 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 blah. Actually, we have already done these cases, and we have already a strategy for this, and we have already a paper and a special case over there. And I think I have an idea for that. And this guy over there has an idea for that. This is how it went. So it really was a program. You can find written accounts of that. Some of it was already done, and then it needed convincing and community spirit to go and tackle the rest. And a lot of it was originally set up in a way that later turned out to be the way it was done in the first generation proof. And then later people came and said, oh, now in hindsight, we know what we can do better.
Yeah, it's just an answer about Lean. For the moment, in the Lean mathematical library, the only simple groups that are known are the cyclic groups of prime order and the alternating group of degree 5. So we are far from having the easy side of the classification.
Baby steps.
I think have been but and so on. And how is the ability?
Yeah, so this is about the interviews. If you could say a bit more about how you, what kind of interview are you using? Do you have a theory? Are you using some of the theories that have been developed for interviews? There are all these. There was also the role of, how do you, you said you have a guideline, so I was just wondering, how did you construct the guidelines and also in the analysis, like the coding and your role in this co-construction that goes on with interviews, and also you said this about memory, and yes, it's just, of course, not just memory, it's also a reconstruction of your own, the self-image, all these things that goes into interviews. I think it is extremely interesting that you actually have this opportunity to, you're not restricted to the written text or sources. You actually have this kind of access, and I think that is great. But so I was just wondering, how far are you in all this, and what are your thoughts about that?
Mm-hmm. I will begin, and then maybe you can take over. Is that okay? Please don't hit me we don't have a theory. I'm very sorry.
Well, we don't use a theory. We have a lot of theories around, of course, but yeah.
Thank you. I approached the community, and then I came up with a set of questions that I wanted to ask everyone, plus some side questions that came up during the conversations. And I kept refining. I kept looking for instances where I felt that the way I asked the question is already leading in a direction, and how can I avoid that, and how can it be more open, blah, blah, blah. So this is very challenging. Plus the mathematical side. So yes, it would be great to have a professional interviewer, but the person has to know the maths. Otherwise, the person might not be taken seriously. So in a way, I felt that my very naive approach might have a lot of, like a big downside, but maybe there are not so many people who can do this. I'm not sure. I find it really difficult, and I see the limitations. So there are the limitations of me as a person, very much because I'm not a trained interviewer, and I basically had to, like, together with Volker, so we came up with a set of questions that we thought, okay, this should be for everyone for some comparability, but then the rest had to be done by me as I went. So there were many personal conversations, there were video chat conversations, I had a few phone conversations before we started officially recording everything, so many conversations off the record, and whenever we had a recording, then we did a transcription. Volker can say more about that. And we even try to convince people to actually make this accessible, but some don't want to. It's really difficult. Do you want to say more on that?
Just add perhaps that because it's time critical, we really thought we should just start out. And unfortunately, time has already proven that that was right. So we really found it was important to just start now, given the fact that quite a few of these people are 80 or beyond.
And I should maybe, because we speak about this, I'm so grateful to the community. I'm so grateful to these individuals who talked to me. Plus, I was able to look at estates. People donated documents to us, to the project. I'm not an archivist, is that a word? So I'm not trained for many of the things I do there, but we do them in this way. So we talk to each other, of course, a lot, and we talk to people who know more than we do, but it's time critical. A few people died. One person died. I had already the interview set, and I was basically already on the train, and then the person passed away.
Yeah, thank you. You're right. It is really, it's almost.
And we are happy to make this process better, and we take ideas, of course.
Thank you.
But do you think we have time for one more question? But then there is time for in the general discussion later.
In many telling of the story of his proof that I am familiar with, including yours, a big deal is made of the announcement of Mason, the classification of quasi-thin group, and the gap. But I don't know about the gap. So can you say more about that? What happened? It was this, I don't know what happened. Like, was this not read carefully enough, or?
Do you understand the question?
Yes, the gap about the quasi-thin case.
Oh!
In 1983, people seemed to believe that the classification was done. In fact, it was completed 20 years later. So there was a very serious gap. But what happened there? Like, did people not read the proof carefully enough, or was the gap very subtle? Like, what happened? What happened with Stone?
Should go back to
Right. Yeah, we can go back. So, what is a proof? At the time, I guess the community thought that it is a proof if we have seen the work being done and we have seen the publications, or we have seen somebody give a talk. So it's not yet published, but we have seen the talk and we believe that everything works. Or maybe someone tells us they have a manuscript and we trust this person because they have done good work before. I don't want to be mean, but partly this was the problem. So it's good to have trust in the community, but at that point of time, maybe there was some trust put in people or their work, or whether they would finish it in time, that was misplaced in a way. And I've even talked to some of the people who were responsible for such gaps, and these are difficult conversations. because you don't want to blame them. You don't want to say, oh, you said you finished it and then you didn't. Sometimes it just turned out to be much harder than they thought. Maybe they had overlooked a special case. Maybe someone else checked it and didn't understand pieces of it. There was a manuscript of several hundred pages that turned out to contribute to what we now call the quasi-thin gap. And if you're interested in more details, then please ask me later.
Yes, and these 2 volumes fill the gap.
Yeah, so that was 2004, and these 2 books filled. So they thought it was done, and now it's 2 books, and I've seen them. It's really difficult stuff. So if you find a gap like this, you cannot just fill it next week.
Should I just say? So in fact, if I understood correctly, what happened is that some part of the proof was way harder than what people originally thought in the 80s.
Exactly. So
and then people realized that there were some argument missing, and when they tried to complete them, it turned out to be a huge work.
Yes, it was a substantial case in the strategy, and people thought it was done because someone said, I've done it, I have a manuscript, and then it turned out, no, it was not.
Okay, so I think we should stop here. Thank you again.
That's great.